Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Basic Electronics 1, and this lecture is entitled Superposition Theorem. Okay, this is actually version 2 of my Superposition Theorem online lecture, because I figured after 81,000 hits on YouTube, it was time to redo this thing. Same stuff, better audio. So if you're trying to link to the old one, chances are you're not finding it. I'm replacing it with this one. Okay, superposition theorem. Superposition theorem is actually one of my favorite electronics theorem because it's no duh. The effects add up. That's it in a nutshell. The effects add up. So with a circuit with multiple sources, one might be led to believe that you got to perform this uber complicated matrix math in the form of mesh analysis or nodal analysis. Well, check it out, guys. Those are just party tricks for nerds. The superposition theorem is a hammer, and we all know the hammer fixes everything. Okay, so superposition theorem, like I said, the effects add up. What this means in more technical terms, the response, the total response, is the algebraic sum of individual responses, linear responses. We'll go into nonlinearity in a second here. So these are kind of the steps over here that I've drawn. It's kind of a flow chart. Basically, you're going to start at number 1, pick one source, and number 2, remove the rest. When I say the rest, how many sources do you have? I don't know. I don't know which circuit you're working on. This one has 2, so we're going to have 2 loops through this thing here. How do we remove a voltage source? We'll replace it with a short. If we have a current source, we'll replace it with an open. Very critical when you're looking at shorts and open, it will change how circuits behave. So we're going to come back to that one. Number 3 is we're going to determine our individual response based off that single source. Now here, check this out. Here's an arrow. It goes back to the top. It's basically kind of a loop. So now you pick the other source, remove the rest. If it's a voltage source, you short it. If it's a current, you open it. Determine that individual response. Are there more sources? Loop it back to the top, loop it back to the top until they're all done. So if you've got 4 sources, you get to do this 4 times. If you got 3 sources, 3 times. Our particular example, we got 2 sources, we're going to do it twice. Now what we're going to do, step 4, is summate the responses. Okay, summate the responses. You're going to take your responses, in their particular examples, current or voltage or whatever, and you're going to add them up. Now I need to put a notification here. Pay attention to direction. And I'm going to underline that, okay? Because you have to, if current is going in one way and the second source is inducing current in the opposite direction, you have to be aware that they are opposing each other, okay? So direction is imperative. And finally, our little note here, the hammer doesn't really fix everything, but it will lead you to the results that you want, okay? Because this is not valid for nonlinear properties, okay? Current is a linear property, okay? Power is not a linear property, okay? So for example, current should go up in a linear fashion. Power goes up in a nonlinear fashion, okay? So you cannot just summate individual powers to get the total power, okay? We'll go into that, and I'll illustrate that with a couple examples. Okay, so here's example 1. Got a 54-volt source on the left, 48-volt source on the right. Which one do you want to do first? Because we're going to pick one source. I don't care which one you want to do first, because I'm going to do the 54-volt first. So I'm going to write in blue. And this is what I recommend you guys do. Get a colored pencil. Do not get a colored pen. No pens in my class. Pencils. Okay? Redraw it as if the 54-volt source was the only guy out there. What do we replace the 48-volt source with? A short circuit, because it's a voltage source. Now, from the perspective of the 54-volt source, let's say, so our end state, we want to figure out the current and the power for the 12-ohm resistor for a 2-source network of 54 volts and 48 volts, okay? So we're going to try to figure out what the induced current is through the 12-ohm resistor. Okay, so in our blue network, our 54-volt source would induce a current, a source current, that would probably travel this direction, given the polarity. At this point right here, it's going to split up between the 12 and the 4, okay? So it looks like the 4 and 12 are in parallel. So I can redraw this network like this. So we're collapsing our network to a simplification. The 4 and 12 are in parallel. 4 and 12 in parallel give us a result of 3. The 24 and 3 are in series, should give us a value of 27 ohms. Okay, so now what is the source current for this incredibly simplified network of resistors? Well, it's a 54 volt source with 27 ohms. IS 54, here's our applied voltage E divided by RT, so 54 divided by 27, it's 2 amps. Okay, I know sometimes you may not have colored pencils, so if you want to go ahead and, because you're going to be doing a number of sources here so you don't get confused, throw a prime in there. I source prime, i.e. the first source. Excuse me, so this is the current induced by the first source, okay? Is that the current through the 12 ohm resistor? Nope, that's the source current. Let's go backwards, because again, we've collapsed it to this simplified circuit. We're expanding it again. Is it still still the same 2 amps there? But again, it's through this resistor right there, which in reality is the 4 and 12 in parallel. So what we get now, here's 2 amps coming into this node right here, and it's splitting up according to the current divider rule. What's the current divider rule say? Well, if I want to know the current through the 12 ohm resistor, and it's a 2 resistor network here, I take the 4 on the top, 12 plus 4, times the current going through it. So basically 4/16 of 2 should give me 0.5 amps. Now, super critical. What's the direction? Down. So according to my 54 volt source, my induced current in the 12, I12 prime, 0.5 amps. And I'm going to put this thing here as a reminder that it's going down. Okay? Don't worry about pluses and minuses just yet. Just say it's going down for now. Okay? We have gotten to step 3. We've determined the individual responses for the 54 volt source. Okay, now what are we going to do? Loop it back to the top. Change our pen colors. So we're going to do the 48 volt source. Okay? Get rid of the 54. What is the 54? It's a voltage source. So we're going to replace it with a short circuit. So 24, a 12, 4, and our original 48 volt source. Well, what's it going to do? 48 volt source, given its polarity, is probably going to induce a low current this way. Looks like in this particular perspective, the 12 is now in parallel with the 24. So not only do you have to worry about this whole short and open changing the circuit, you have to look at from the perspective of those sources, those individual sources. From the perspective of the 54 volt source, the 12 was in parallel with the 4. From the perspective of the 48 volt source, the 12 is now in parallel with the 24. So it gets a little bit more complicated when you're switching sides back and forth. Okay, so let's go ahead and do our similar steps. We're going to collapse 12 in parallel with a 24, do the calculations. And by the way, you can follow along. Please, by all means, stop the video and, okay, do the 12 divided by 24, 12 in parallel with 24. And see if you get 8. Certainly hope you did. Okay, here is now an 8 in series with a 4. What's an 8 in series with a 4? I will punish you if you have to use a calculator for that. It's a 12. Okay. Current's going in that direction, 48. Okay, so what is our I source? Red, or if you may be using one colored pencil, call it a double prime. It's our induced voltage divided by our total resistance. So 48 divided by 12, that's 4 amps. Okay, so it's going in that direction, in a clockwise direction. Let's go expand. We're going back. So we've collapsed, collapsed, collapsed. Let's expand back to our second level. That's still the same 4 amps. And according to, we're going to expand one more. So that's our source current of 4 amps coming into that particular node. It's going to split up according to the current divider rule between our 12 and 24 in that direction. What's the current divider rule for that? Well, it's 12 plus 24. And if we're solving for the current through the 12, put the 24 on top, what is the current coming into that node? It's 4 amps. So 24 36 of 4 amps should give us 2.67 amps. Critical point, going up. Okay? We have basically determined the individual response for the current through the 12 ohm resistor given the 48 volt source. I'm going to put that answer right up here. I12 double prime, 2.67 amps up. Okay, so we have reached the end of our loop there because we are out of sources. We've done both sources. And now, number 4, summate responses taking into consideration direction. Okay, so let's switch our pens again. I12, the final I12 that we're looking for, is equal to the algebraic sum of the individual responses, I12 prime, I12 double prime, taking into consideration direction. Who wins, 2.67 up or 0.5 amps down? Pretty obviously 2.67 up. So what I'm going to do is write this in this direction is double prime 12 minus single prime 12 should give you 2.17 amps. Which direction? Going up. Okay, so what is the power for this? Okay, I said it's not valid for nonlinear properties. What I mean is I could not use this current to determine the power. And this current to determine the power. Okay, whoops, sorry, I made a mistake here. I could not use those two currents to determine the power. I can, however, use this current to determine the power. Okay, because that is what the current through that 12 ohm resistor it is. It is 2.17 amps going up. So I should be able to figure out power for the 12 ohm resistor is equal to I squared R. So I squared, 2.17 squared times R, 12, should give me a total of, 1 moment, 56 watts. Okay, so if I did try to do the power individually, say for example, I squared R, so if you will, P double prime 12, I squared R, that's going to give me 2.67 squared times 12, which is equal to 85 watts. And if I was to try to do this one, P single prime 12, if you will, I squared R, 0.5 squared times 12 is equal to 3 watts. We can already see that 85 plus 3 is most definitely not equal to 56 watts. Okay, so we can determine individual responses, individual linear responses using our method, but we got to wait to the very end to determine something like a nonlinear property like power. Okay, so that's one example right there using my particular method for the superposition theorem. Again, it solved it. Quick, easy, it's a flow chart. And it's not that much to remember, really just 4 steps. Okay, so I'm going to go ahead and make another example and we'll go ahead and see if you can walk through it. Okay, so here is our second example. It looks like we've got another 2-source circuit with a 36 volt source on the left. In this particular case, it's a 9 amp current source on the right. Okay, so again, pick one source. What do you want to do? Let's do this 36 volts. From the perspective of 36 volts, what does this circuit look like? Still's got a 12 and a 6 ohm resistor in that fashion, but I've taken out the current source by replacing it with an open. How does this change the network? Okay, well, it's an open. Here's this tremendous gap right there, and there's no way Johnny Electron can get from the left to the right, or excuse me, from the top to the bottom in this particular case. So there is no current in this branch right here, no current in this leg right there. Okay, there's no way an electron can get from the top to the bottom. Might as well just take it out. How easy is this? It's the 36 volts with a 12 and 6 in series. Got a source current, IS prime, going in that direction. Simplify it again. It's an 18 ohm resistor. What's our source current? IS prime is equal to our applied voltage E divided by our RT. 36 divided by 18. 2 amps. Which way is it going? Down. Now let's say, for example, we're looking for the current in the 6 ohm resistor. It's in series, so it's still 2 amps. So let's put that result up here. IS single prime, 2 amps, going down. We have determined that individual response. Okay, let's go loop back up to the top, pick one source, 9 amps. From the perspective of the 9 amp source, we see 6 ohm right there, 12 ohm right there. We replace our voltage source with a short. Oh my gosh, look what happened here. The 12 and 6 are now in parallel, as opposed to over here where they were in series. Okay, so putting opens and shorts, like I alluded to earlier, can change the entire functioning of the circuit depending on the perspective of that particular source. Okay, so 9 amps, this is a pretty simple one. We don't even need to really bring it down to a more simplified fashion because we're looking for the current through the 6 ohm. Let's just go ahead and do a current divider rule. Here's definitely 9 amps coming into that node. It's going to split up this way and this way. There's going to be more current going through the 6. So again, because if you get an answer where there is less current going through the 6, you know you did it wrong. Okay, current divider rule. 12 plus 6. The 9 amps coming in. I6 prime, double prime, excuse me, because this is our second source. And because we're looking for the current through 6, we put the 12 up there. So 12/18 of 9 should give us, 1 second, should give us 6 amps. Which way is it going? It is also going down. Okay, so here is our, we've already gotten to the I6 double prime, 6 amps. We've already determined that individual response. And by the way, just notice something here. That should be a 6, not an S. It is S technically because it is a series network when viewed from the perspective of 36, but let's just keep apples with the apples. It's the current through the 6 ohm resistor. Okay, again, now we've determined the individual responses from our perspective of our two particular sources. Summate the responses, making sure we indicate direction. They are both additive, they're same direction. So what is our final current to our 6 ohm resistor? It is 8 amps going down. Okay, what is the power dissipated by our 6 ohm resistor? It is I squared R, 8 squared 6, 384 watts. Again, I'm using the final current to determine the nonlinear property of power. I cannot use the individual currents in Summit to get power. That's it, guys. That's superposition theorem. We are going to be making use of the superposition theorem a lot. And we're going to be making use of the superposition theorem in another theorem called Thevenin's theorem, which you guys will be using over and over and over and over again. Thevenin's theorem is not superposition theorem. Superposition theorem is not Thevenin's theorem. There are two independent theorems which can be used together. Okay, we will use superposition theorem to determine Thevenin's theorem results. Okay, so before you step into the next series of lectures, I definitely recommend you knock out the superposition theorem. You need to perform examples of this. Find examples within your book, in workshops, in examples online, in the back of your lab. Work on examples with superposition theorem. Get comfortable with this before you move on to the next series of lectures, which again is our Thevenin's theorem.